Okay, welcome back to Real Analysis. We're continuing in our work in Chapter 5. In this section, we're really going to start getting into some of the results that will seem pretty familiar to you from your first semester calculus course. So in particular, in this video, section 5.7, a short section, it'll be a short video, we're going to talk about something called the extreme value theorem. So the extreme value theorem was something that you certainly met in calculus, and you did lots of applications with it anytime you were finding minimum and maximum values of continuous functions on closed intervals, of course using the derivative and critical points and some other theory. But this theorem was the kind of underlying basis that you were always going to be able to find answers to those problems. All right, so let's take a look at it. It's theorem 5.50 in your text. I've kind of restated it here and given it a name, the extreme value theorem, or we can just call it the EVT. So what does it say? It says if you take a continuous function f on a closed interval, so here a and b are two real numbers, the usual kind of closed interval convention. A and b are two real numbers, b is bigger than a, continuous function f on there. Then there exist two input numbers, and hopefully the notation is not off-putting here, but I'm calling them x lower star and x upper star. So they're two numbers that you can find in this interval in the domain of f, and they have the property that the output at f lower star is less than or equal to any other output f of x, which is less than or equal to the output at f upper star. Okay, so that's true for all of x in the interval. So in the language of calculus, maybe I can just sort of squeeze it in here. X lower star is called a global minimum. And X upper star is called a global maximum. For the function f. So a global minimum, by definition, is some point in the domain whose output is less than or equal to every other output. And likewise, a global maximum is some point in the domain whose output is greater than or equal to every other output. All right, so the extreme value theorem is saying that a global minimum and global maximum for a continuous function on a closed interval always exists. Okay, and in Calc 1, you learned how to look for these possible global minimums and maximums using the differential calculus. And we'll continue that in this course as well when we get into the derivative in later chapters. Here, we're just going to establish the existence of these things. So we know that we're not going to be looking for something in vain. Okay, proof is going to go pretty quick, but it's kind of a nice exercise for you when we're done with the proof to stop and kind of explicate how much machinery is going into this thing. It's going to kind of feel like it goes pretty smoothly because we have built up an enormously large amount of machinery to prove such things. Okay, so let's get going here. So we'll take our continuous function f on this interval from a to b, and then I'm going to start by using a kind of recent result, theorem 5.49, that says this continuous function is bounded. Okay, continuous function is bounded on a closed bounded interval. Okay, so I can speak about the supremum. If I look at the set of outputs f of x, where x goes from a to b, the supremum of that thing is a real number. It's a bounded set. Likewise, the infimum of it is a real number. So I'm going to call that supremum m and little m. Okay, so I know right away that the outputs f of x are at least little m and no more than capital M. But what our goal is to show is that those outputs actually get obtained. So I need to show that there exists these numbers, x lower star and x upper star, such f of x lower star is equal to little m, and f of x upper star is equal to capital M. Okay, it's that latter one that I'm going to focus on. I'm going to leave as an exercise to you to kind of modify the proof I'm presenting here to produce the global minimum. Okay, so I'm going to focus on the global maximum. Okay, so to continue on the argument here, going way back to the definitions and when we worked with supremums. If you give me a natural number n, its reciprocal is a positive number. So if I subtract that from the supremum capital M, I get something that's less than capital M. Okay, and any number that's less than a supremum cannot be an upper bound for the set. Okay, so this number m minus 1 over n, it cannot be an upper bound for the range of f, the set of f of x, where x ranges over a to b, because it's less than the supremum. Okay, so if it's not an upper bound, That means I can find something in this set, something in this range that's bigger than it. But something in this range looks like f of something. So because all of this depends on this natural number, if you roll all that together, for any natural number, I can find an input. I'm going to call it x sub n because it goes with the natural number, such that its output would be strictly bigger than m minus 1 over n. I can do that because m minus 1 over n is not an upper bound for the range. This other inequality, well, that's true for every x in the domain because m is the supremum. Okay, so stop the video for a second and let that kind of soak in. For every natural number, I can find an input value in this interval that these two inequalities hold. So since I can do that for every natural number, I've built a sequence. I've got a sequence of points in this closed bounded interval a to b, this compact interval a to b. Well, that interval has the Bolzano-Weierstrass property. 4.21 is the reference I'll cite to remind you of that. If it's got the Bolzano-Weierstrass property, it means that that sequence xn has some convergent subsequence, call it xnk, and the limit of that convergent subsequence is in this interval. Very important. So it converges to some point that I'm going to suggestively call x upper star, and x upper star is an element of the domain of this function. So not to give a plot spoiler here in the proof, but I'm going to show that f of x upper star is equal to capital M. That's my goal. So x upper star is going to be our global maximum. Okay, so how am I going to achieve that goal? Let me just scroll a little bit so you can see the proof. How I'm going to do it? Well, I'm going to use the continuity of f. I'm going to apply f to that convergent subsequence x sub n sub k. The image sequence has to converge to f of x star. That's by continuity. Okay, but we said above that every one of these function values, it was on every n, so in particular the subsequence values, it's no more than m, but it's greater than m minus 1 over n sub k. Maybe I'll write in here parenthetically somewhere. This is where I've got the room. N sub k goes to infinity as k goes to infinity, right? Subsequence terms have indices that get as big as you like. So as k goes to infinity, this expression m minus 1 over n sub k is going to approach m. Yeah, the constant sequence m certainly approaches m, and our sequence, our image sequence f of n sub k is between them. So busting out another tool. If you're explicating this proof, here's another tool. I'm going to use the squeeze theorem for sequences. Using the squeeze theorem for sequences on those inequalities that are written right above it, we can conclude that the image sequence f of n sub k has to converge to m because it's trapped between two sequences, both of which are converging to m. Okay, but we already said that this image sequence converges to f of x star. Well, so once again, a piece of machinery. We have uniqueness of limits. It was theorem 2.8. Uniqueness of limits of sequences says that those two limits of this same sequence have to be the same. A convergent sequence only has one limit. So there you go. F of this point, x upper star, which we've established is in the interval from a to b, is equal to m. M is the supremum of the range, and so certainly it's true that f of x is less than or equal to f of x star for every x in AB. Nice. So I hope you will take the challenge here. I'm going to leave writing the proof of the existence of x lower star as an exercise, right? So you're going to have to take that little m, that infimum, maybe add something to it like 1 over n. That can't be a lower bound, and so on and so on. So it's an excellent chance for you to kind of make sure this argument is digested by seeing if you can walk through making the appropriate changes to write a proof that there's some number x lower star in this interval, that its image f of x lower star is less than or equal to f of x for all x. Okay, so that's our extreme value theorem. This video is going to be a little short. I'm just going to kind of, well, so actually, sorry, a couple comments here. It'll still be short, but as a couple of comments, that the closed and boundedness in the argument are crucial. So just to kind of bring up some of our similar old examples, that if you take a function f on the open interval from 0 to 1, the reciprocal function, that's continuous, but it doesn't have a maximum value. You can't find an x upper star that is greater than f of it is greater than or equal to f of any other x. That function's unbounded on that interval. So the closed part is crucial. If you take the identity function on the closed interval from 0 to infinity, it's closed but not bounded, right? That also has no maximum value. So the fact that the interval is closed and bounded is crucial. If you take away either one of those ingredients, then you can write a continuous function down that doesn't have a global maximum in this case. You could also modify these examples to come up with things that don't have global minimums. Cool. You could modify these examples to come up with functions that don't have either one. Those are good exercises to come up with. Can you come up with some function on an open interval in the real line that has neither a global minimum nor a global maximum on that interval? I'll bet you can do it. Okay. So here, the end I wanted to just that I started saying earlier is that kind of as before, I'm stating and proving all of this stuff for closed bounded intervals, but really the kind of crucial part of the ingredient was invoking the Bolzano-Weierstrass property, that a convergent sequence has a sequence has a convergent subsequence whose limit is in the set. That Bolzano-Weierstrass property is valid on any closed bounded set, that is on any compact subset of the real line. So really the extreme value theorem that we just proved could be stated on any compact subset of the real line for its domain. That's what the theorem 5.52 says, although the author is writing f is continuous on a closed bounded set A, but let me just remind you that a closed and bounded set A, that's basically saying the same thing as a compact set A. Right? So a continuous function on a compact set has a global minimum and a global maximum. That's what theorem 5.2 says. I'll let you kind of walk through. I gave the ideas, but you can walk through the detailed written proof as an exercise. Okay, so that's it for this short video. Thanks for listening.